Good afternoon, everyone. I also second Professor Marcio's comment about the exciting topics that we have the next couple of days here. It's really tough sometimes to come up with the new topics and or trying to advance the state of the art and what we do. But I think we are proving that we are more than capable of doing this. So I'm looking forward for the rest of the conference myself. I would like to acknowledge the co-authors of this paper. In fact, Dr. Olga Alexandrova, she was supposed to be here. She got stuck in Russia, and she was not able to make it on time. But she's a chemical engineer and a chemist that actually did a lot of work in the study. Also, Professor Jonathan Allen. He's a colleague in the Civil and Environmental Engineering Department, and also has a joint appointment with the Chemical Engineering Department at ASU. And then we have our three graduate students who actually do all the work in these studies. Kinyu Sun, Carolina Rodezno, and Daniel Gonzalez. And one of them is actually Carolina Rodezno. If you raise your hand back there, she's present with us here today. Well, you heard so much about I don't know if I can top what George has gave us a good background on the asphalt rubber hot mix in Arizona, but I have just 3 points, just bear with me. Sometimes repetition, it might be good. The policy of the state of Arizona to recycle and reuse waste tires, and this has been going on since 1990. And a big usage of these tires are used in the asphalt rubber hot mix. And the Arizona Department of Transportation, one of the leading states, has actually been long supporting these activities. I think it's very obvious what we have seen so far just today, that these asphalt rubber mixtures are actually performing very well, very successful in the field. And I think the caliber of the researchers that we have in this gathering are able to show the quality through laboratory tests and field experiments as well. I prepared this slide to show you, and it's by no means this is a very comprehensive effort of what's going on. But when we talk about the asphalt rubber, asphalt concrete friction course, and what we do at Arizona State University in terms of trying to understand the behavior of this material. We have done some binder performance studies, looked at the binder modification and how it really improves upon the viscosity temperature relationship in the high temperature as well as the low temperature. We looked at the mix performance, and I think today we have seen a couple of very good examples on the mixture performance and how the AR2006 actually perform in the field, as well as we can capture that in the laboratory. You will hear later on in this conference about noise issues. Has been touched upon earlier, but I think there is more in-depth papers, technical papers, looking at why the ACFC actually reduces the noise in the field. What can we do in the laboratory to capture that? So there'll be exciting couple papers on that later on. The urban heat island, Mark Belchi presented a very good overview of the heating phenomena or mechanism of pavements, especially in urban regions. The thermal blanket effect, that's actually really helping what's underneath. That's another important area. I've seen, and we have done before, life cycle cost analysis. You pay upfront more for these materials, but if you look at the life cycle cost and maintenance issues, you always come on top as a winner. And today, in the next 10, 15 minutes or so, I'll talk to you about tire wear emission. How are those surfaces contributing to the air quality that we have in urban regions? This project actually started, 3 years ago. I don't know if George Way is here. We've been walking one time after a meeting and discussing with Professor Allen, most of the dust that we have in the valley, it's not really only dust. There's a lot of particles, a lot of pollution comes from tire wear. So we were kind of contemplating and thinking, well, can we do something to quantify that? And the whole idea is, when we thought about it, is looking at, can the actually asphalt rubber, asphalt concrete friction cores, the road surface layer, result in less tire wear? And in fact, this is what we were thinking. It's actually going to produce less tire wear. And here I'm not picking on the Portland cement concrete mixtures because we do a lot of work in this area as well. But it just happened that most of the highways we have in the valley is Portland cement concrete, and they are being overlaid with ACFC for noise mitigation. So we have designed 4 tasks. The first one is looking at the particulate matter, PM. And if you are an environmental engineer, you know exactly what that means. But these are emissions from the on-road vehicle traffic, again, during typical rush hour conditions on a highway. And the idea is to, can we do this for an ACFC and a PCC, before and after the overlay? We were to collect and analyze in order to determine what some of those pollutants we have in the aerosol samples. We needed to actually do some chemical analysis on the tire tread themselves, trying to identify what are some of those tire wear markers, what are the chemical compounds that we can identify in our samples when we collect it. So that was an important task to include in the study. We analyzed the PM emissions. We determined some factors, and we were able to determine the tire wear emission for the different road surfaces. So this is the analytical part, if you wish, as part of the scope of work here. And then finally, we were interested to quantify something we have known or we have seen before, but we thought it's a good opportunity to look at the roughness and the friction characteristics of these 2 different types of surfaces that we have. Just a couple descriptions. On the PM itself, it's regulated by US EPA. You heard about this in the opening session, the lady from the EPA. It has been shown also to affect human health, actually worsen the air quality around in the urban areas. And a lot of times when we talk about PM, we refer to sizes, PM10 or PM2.5, and these are in microns. So again, very minute, small particles in the air that's suspended in the air. Vehicle emissions are a significant source of both PM2.5 and PM10. If you consult the literature, a lot of studies, not specifically exactly what we have done here, but they talk about the contribution of the different pollutants as part of the PM2.5 and PM10. Advancement in vehicles that we have, even if we go to a zero emission, talking about vehicle emission in this case, you are going to still generate some of those PM because of the tire wear, road wear, brake wear, and so forth. And even some of the resuspended dust that we have aggravated by the traffic. Typical values for tire debris, in the literature, you're looking at about 5 to 7% of that PM10. So the rubber loss, it's really a function, or we believe it's a function of the road surface type, or at least this is the hypothesis that we have in this study. Driving conditions might be also another factor. Traffic really moving at a constant speed, or they are really stop and go situation. So these all have to be watched, for. And even the tire conditions might be a factor in some of those emissions that we have. Here are some numbers. Estimate average about 90 milligrams per kilometers, or that correspond to about 1.3 million metric tons per year for the entire US. It's quite a significant number if you think about it. Tire wear emissions are so important for the EPA. The EPA used the tire wear emissions, which indicated by tire, and this relationship over here, they use the Mobile 6.1 model, and again, to estimate the tire wear emissions. And you can see the 2 components that goes to the fractional particle size, the cutoff size, and the number of wheels. Use that in the formula to estimate the tire or the tire wear emission, TIRE. For example, a passenger vehicle is estimated to emit about 13 milligram per kilometer of PM10 and about 0.13 milligram per kilometer of PM0.1. Again, I just want to paint a picture about the size or the quantities of the measurements we are doing here in the study. So the Mobile 6.1 can be used to estimate the air quality for air quality modeling. And the only thing, for example, is we have never measured anything like this for asphalt rubber pavement, so we don't know what these numbers are. So it's always good to, if we can get the measurements, we can have a better prediction in these models. Here is the experiment. Some of you probably are very well aware of the Deck Park Tunnel on the I-10 in the Phoenix, Arizona area. The picture is here on the left-hand side, the bottom there. This is the eastbound entry, actually, of the tunnel, just to give you an idea what it is. And if you look at the right-hand picture there, it's on top of that tunnel is actually a park. That's why it's called the Deck Park Tunnel. The picture in the middle shows the tunnel. And no, I did not stand in there, took this picture during traffic. It was closed for paving. You can see one lane of this rubberized asphalt has been placed on the right-hand side. So there were two measurements that were done at this tunnel at 2004 and 2005. We waited for about 1 year. We wanted to get all this initial wear from the surface of this material out of the question so we can compare only tire wear issues. And then again, this really was a good opportunity. ADOT was using, or this was implemented in the Quiet Pavements program because of the noise mitigation, and we just really took this opportunity to do the measurements before and after. Measurements, my colleagues, chemical engineers, they say it's rather simple. You use all this equipment. But what it is really, it's a cascade compactors. It looks something like this one over here. You put one at the entrance of the tunnel, and you use that as a reference for measurements, or somewhere location where really you're not affected by the particles as much. And what you see over here is actually the exhaust chimney. Got a few of those on top of the deck itself in the park. And again, we have coordinated this with ADOT to collect air samples by turning the fans on. And these fans usually are turned on in case of an accident. The temperature is different in the tunnel itself. So, and you can see here, the aerosol sampling is being conducted from that chimney. It goes into a trailer, it goes into another compactor. What's in this compactor here is a bunch of filters that actually can separate the different particles, that they can be taken back to the lab and analyzed chemically. Along with that, CO2 concentration also were measured at the tunnel. They were able. And again, you see all the equipment that's housed in the trailer that is collecting all this or the PM. An important factor in the whole issue here is you want to make sure that you have the same traffic volume, same traffic type in 2004 and 2005. So what we did, we actually had to videotape. ADOT has some counting loops in the tunnel, but we were not sure. They go on different times. We were not sure we're going to capture when we are there capturing the aerosol samples. So what we did, we relied on video cameras to collect this information. Carolina can witness, it's really a laborious work trying to take this video, put it back into a computer, and actually do a manual count of the traffic classifications and vehicles that we have. But what you see here is the westbound tunnel with the traffic exiting from the tunnel that is actually being videotaped. Here is, we use the federal highway classification. We did some little adjustments. We thought it's really okay to do this by grouping some of those vehicle types, 5, 6, and 7, with the federal highway guidelines. Same thing for group 6 and 7. And so we did the measurements as the date shown, May 27 and May 28. Came back in 1 year, and about June 9th and 10th, we did the same measurements. I'm talking about the traffic volumes here, along with the aerosol sampling. And we went through the whole analysis. We concluded that the traffic was fairly constant during each hour, actually, of the sampling period. And also, there is no substantial difference between the 2004 traffic and 2005, which was good news. We don't have to really make any adjustments in the calculations based on traffic. One important part doing the chemical analysis, trying to understand when we get this aerosol samples, how we are going to identify which PM out of those is actually related to tires. So we were looking for tire wear markers. We had to go to the crumb rubber manufacturing plant in Queen Creek, Arizona. We sampled about, 30 tires or so from passenger vehicles, from trucks, larger vehicles. We gouged the threads, we collected that material, and we come back to do the analysis in the lab. What we were looking for is the two famous compounds, and no, I'm not going to try to pronounce these. The 24-MOBT and the NCBA. These are historically related to, by researchers worldwide, relate those back to tire wear markers that can identify that the compounds or the PMs in the samples are actually related or came from tires. The analysis showed and agreed really with some other work that has been done in Japan and the US and somewhere else. It's about 2.3 parts per million in particles of the 24-MOBT. We used also to identify the chemical compound and just to assure us, use a chromatography, gas chromatography and mass spectroscopy, GCMS, and basically this is a device that can chemically identify the compounds that we have being analyzed. So if you're a chemist, you want to do this to make sure that these are the products that we have. There are such other organic compounds, and we touch upon those in the paper, but basically we're looking for some of the other organic compound that might be present in the sample. They can actually be misled, or they can actually serve as tire wear tracers. So we'll make sure we can identify those. And we did. We found the aromatic rings, nitrogen and sulfur as additional compound in the samples that have to be identified and separated in a way. The tire wear emission rates were calculated. You can use now the tire wear markers or traces we have got from the tires themselves. We can compare that to the fraction that we have in the aerosol samples, and we can calculate the tire wear emission from the inflow and the outflow in the vent in that simple formula that you have here at the bottom. Now those 24-MOBT and the NCBA markers, the analysis showed that they are marginals in terms that they are right at the detection limits, what chemists believe they are at the detection limits. Thank you. So what Dr. Alexandrova did, she was really brilliant. She went back and she was trying to find other markers in the study to see if we can identify other compounds that we can rely on as a better indicator of what's going on. She identified two compounds, number 3 and number 4, referred to in the paper. And she also identified those compounds, which is very important, in those tire tread samples that we collected as well. So we make sure that we have the same compound in both locations. Then what she also, she and Dr. Allen, they both worked on the California tunnel, I guess, the Caldecott tunnel, and they were able to identify that compounds also came, or they were present at that tunnel as well. They could not determine the specific chemical names for them. That's why they refer to them as compound number 3 and 4, but they are chemical particles that were classified and they were used as tire wear markers or tracers. And this is really a summary of the results. And the bottom line, because of time here, I just was showing the 5 minutes mark. If you look at the bottom table, the compound number 3 and 4, which we believe they are the tire markers in the sample that we have collected, you can see the experiment 1, which was on the PCC road surface before the overlay. And I'm looking at this part right here. And you can see the micrograms per kilometers calculated from that, 354. And I don't know why you don't see that very well. In my screen here, it says 177. You can't see it there. So this number here is 177. So this is before and this is after. And again, there is a difference in the tire wear emission rates calculated based on those two compounds before and after. PAH, or the polycyclic aromatic hydrocarbons, if you are a chemist, you would like to make sure, or you will run this to assure you the quality of the measurements that you're doing. And again, everything we're doing here in micros, so you really have to spend a lot of effort trying to assure yourself that the measurements you are doing is actually exactly the true of what they say. So she identified about 8 organic compounds, and basically the conclusion from this analysis here that it's really support the analysis that whatever tire wear emissions calculated in the previous tables, they hold true. Roughness, if you look at the IRI, inches per mile, against something we have seen a quite substantial drop, less than half, average about 95 inches per mile to about 45 or 50 inches per mile. And again, before and after, this was the ADOT profilometer used, and these are the measurements before, these are the measurements after. And they were done for each lane along the tunnel itself. Same thing for the friction value. ADOT uses the mu meter. It's a wet friction test. Again, this is a porous material. You expect better friction values, no surprises there. And in fact, you have better consistency in the friction values that has been obtained after comparing to the before. Almost done. Conclusions. So we concluded from the study, and again, it's probably 20 minutes of presenting this, and even without Olga being here, it's probably unfair for the amount of work that really took place in this. But we have identified the tire wear tracer compounds. In this analysis, we have concluded that we have actually provided to the state of knowledge about the procedures or the protocols that to follow in order to do this. That's very well documented in this paper. And we found out that the emission rates of tire wear tracers were higher before at the PCC road surface comparing after the overlay with the ACFC. And they were about 1.5 to 2 times higher based on the calculation that we have done. We believe that these findings will potentially give ADOT now some numbers to go by, which we did not have before, so they can use in the new air quality models that we have for the Phoenix airshed. And again, no surprises there. Roughness and friction characteristics of the pavement surface, they are improved as the numbers indicated. And I will end with this slide here to acknowledge the many people that actually contributed, especially from ADOT, doing or helping with this work in different capacities. And special thanks for George Way for really helping out with developing this idea in the early stages before he retired from ADOT. So with that, I will conclude, and thank you for your attention.
We are open for discussions. We have 10 minutes, and we hope to have interesting discussions. That's the most important part of the conference.
And if you can also introduce yourself if you are a chemist or not, so I know how to answer you.
No, I'm not a chemist.
Good, thank you.
Way. Is there any, did you ever figure out why the emissions were much lower? I mean, if the friction you said was higher, but it seems like it was, I just couldn't see why you would get lower emissions with that surface.
Why you get lower emissions?
Yeah, did you guys come up with some kind of conclusions why it's behaving that way? Or?
I mean, you end up with a smoother surface, better texture. The existing Portland cement concrete, and I don't know if George is here, how old is that tunnel? 10, 12, 15 years? 15, 16 years, George is saying. You saw the roughness measurements before and after. So all of these actually contribute.
So it's wearing, it's just, the PCC pavement is wearing those little particles off every time that.
Exactly.
A little bit more.
In a way, they act like maybe the grooving that we have, different locations, and the roughness will both combine to produce more tire wear.
What about for a new PCC pavement compared to this? Would that?
I don't know. And again, I think what you have to realize, this was a one-time measurement that we have done at that specific tunnel. Other researchers have done something similar, but nothing related to the asphalt rubber pavement. But I can't answer that. If it's a newer surface pavement, perhaps with a longitudinal tining instead of transverse tining, would the results be the same or not? I'm not sure.
Yeah, because the IRI should be just as low on a new PCC pavement. I mean, the reason you're probably getting a higher IRI is it was probably a faulting or something like that. So.
There were some cracks, so there might have been some different weary spots here and there. But again, the IRI were not excessively high. They were still, about under 100.
Low. Yeah, it's
but typically in the valley, when we do the ACFC, those numbers are reduced to about 40 or so. And again, just because of the contractor's ability to construct these 1-inch layers and produce a much smoother surface comparing to what we have.
Yeah. Okay, thanks.
Other questions? Of course.
If I can just comment on his question. We actually have experience in a concrete road in Portugal, which was in very bad condition. Not bad, it was rough. It was a rough ride. Another way of looking at it is the people we do consulting for that, to maintain that highway. It's in Portugal, toll road. And the road was in such a bad condition that they had to change a set of tires every year. Those that had to travel on that road to go to the work. When we overlaid with asphalt rubber, their tires last much longer. But I think the problem is not associated with the roughness itself, not with the friction, but it is with the roughness. What they say it was happening is sometimes the tire would just not be directly on the pavement, goes up and then it comes down again. It's like the same effect you see when the airplanes land. You have smoke coming out because of different speeds between the car speed and the tire speed. I think a phenomenon like that is happening. The roughness of a pavement is causing the tire wear, not the friction. I know this kind of bold step forward in this statement, but my gut feeling goes that direction.
We still have time for a final question.
I'll ask the question, what about wet performance then of such a smooth surface? Does the car hydroplane skid at a lower speed?
Not for the ACFC. And again, you saw the videotape presented by George. The porosity of these pavements will have tendency to drain the surface water much faster than Portland cement concrete or conventional asphalt. And we see that actually even in the Phoenix area. So skid resistance are good just because of that.